right, let's go. What's up, everybody? Welcome to the Comet ML office hours. It is Wednesday, February 16th, 2022. This is the seventh session in our series of standardizing the experiment. I'm super excited for this last leg of the journey. Thanks so much for joining us today. You guys might notice a change of scenery. I'm chilling here in Elk Grove, California, outside in my parents' backyard, so I apologize for any background noise that you may hear. Hopefully my voice will overtake all of that. But yeah, I'm excited to get into the presentation. Today we've got a presentation followed by just a quick little panel discussion with our in-house experts, where we're going to talk about the working sessions that we've done. If you're joining us on LinkedIn, if you're joining us on YouTube, or right here in the room with us, feel free to ask questions at any point during the session. We are more than happy to take your questions. So without further ado, let's go ahead and jump right into it. Let's get into our slideshow. So Austin, if you wouldn't mind pulling up the slides for us. So it looks like we now have our presentation up. So let's go ahead and get with it, man. All right, guys. So look, if you've learned anything over the last few weeks, last 6-7 weeks, it's developing machine learning models can quickly become a messy, complicated process. So when you're a hobbyist or a learner working on a side passion project, you often don't need to worry about tracking or recording your experiments, reproducing your results, or looking up previous model runs, or collaborating with other people. You can get by perfectly fine with scratches of handwritten notes in your Moleskine notebooks or notes in the markdown cells of your Jupyter notebooks. But these practices don't cut it in an enterprise environment. So whether you want to go pro, level up in your career, or start leading machine learning teams, you'll need to develop some good habits and understand some best practices. So let's go ahead and get into some of those in the next slide here. So again, developing machine learning models at scale for enterprise it's an iterative, experimental, collaborative process that can become messy and hard to manage. So as a first data scientist in an enterprise, I've experienced firsthand the pain of not having guidelines and best practices in place for my model development process. I've had to go back to the drawing board after the model I've deployed started degrading in production. I've had to traverse strings of code that I wrote, thumb through actual physical notebooks, control effing my way through text files, and going cell surfing through spreadsheets, searching for clues and trying to figure out what the me from 6 months ago was thinking when I built this model. But I don't want you guys to have to go through that same headache. There's a quote from John C. Maxwell that says, "A wise person learns from his mistakes, a wiser one learns from others' mistakes, but the wisest person of all learns from others' successes." And so today I'm going to share lessons that will help you standardize your experimental process quicker so that you can formulate, test, and evaluate hypotheses in rapid speed for your problem statement, and then hopefully build better models faster. So a quick preview of what we're going to discuss over the next few minutes here. We're going to talk about an overview of the machine learning model development process. We're going to talk about how managing your how to manage your experimental runs like professional. We'll also talk about iterating and experimenting with algorithms, and then we'll talk about hyperparameter search and fine tuning. Let's go ahead and go to the next slide. What you'll see here on the next slide is the typical machine learning workflow, right? Machine learning is iterative. So if you've been following along in this series, then you've probably heard me say it at least 42 times. The machine learning lifecycle is iterative and continuous. So implicit in this continuous process is a feedback loop that will help you improve. And that's because results from later stages in the pipeline are informed by decisions in the earlier stages. But what does a feedback loop look like? So whether it's CRISP DM, OSEM, or the Microsoft TDSP, all machine learning lifecycle frameworks really at the core of it involve 6 activities. And you'll see those 6 activities right here in this diagram that I drew for you guys. It's a process of understanding the business problem or research question and identifying data that is relevant to making progress against that problem. The second is preparing data through some process of ingesting, integrating, and enriching that data. And this is usually through some combination of data pipelines for ETL processes and feature engineering. Third is representing the data generating phenomenon using statistical and machine learning algorithms by finding a model of best fit. Fourth is evaluating the model and testing it to make sure that it's able to generalize to unseen data points. Fifth is deploying the model as part of some application or some larger system. And sixth is monitoring the performance of that model by measuring and assessing its effectiveness, as well as monitoring the statistical properties of the data that come into the model. Then you get to repeat this whole process over and over again. Because, as Andrew Ng says, machine learning is an empirical process. Being able to go through this loops many times very quickly is the key to improving your model performance. So let's go ahead and get into the next slide, where we're going to talk about the case principle. Can't recall exactly where I heard this, but it must have been in one of the previous weeks that we've chatted. But if there's anything true about the machine learning process, is that it abides by the case. So what is the case principle? It's changing anything changes everything. And this is the phenomenon by which change anywhere in the machine learning process, especially those changes that are furthest upstream, will have unanticipated impact on your experiment and your results. So this brings us to our next topic, which we'll talk about in the next slide, which is experiment management. So here's a quote here by Andrew Ng. But it's the common saying about machine learning is that it's when code meets data. And a common saying about code is that it's read more than it is written. But in machine learning, reading only the code doesn't give you the full picture. So you're probably wondering, isn't Git enough for all of this? Yeah, version control is absolutely necessary, but you'd only have access to the information that you care most about if you ran the code from start to finish. And so this could take hours, days, weeks, or if you're Tesla, it could take a year. But when running machine learning experiments, you care about much more than just the code. It's everything beyond the code that you'll be most interested in. That's the hyperparameters, the metrics, predictions, dependencies, system metrics, training artifacts, and so much more. So having access to all of this allows you to understand differences in model performance and iterate towards a better model. So what should you be tracking for your machine learning experiments? So like anything in machine learning, the answer is usually, it depends. But I'll share some advice that the godfather of machine learning himself, Andrew Ng, shared in his course, Introduction to Machine Learning Production. And then we're going to go through that right here because he recommends keeping track of 4 pieces of information, which we're going to see right here in the next slide. So the things that you need to keep track of during the experimental process, first is keep track of the algorithm you're using along with the code. Having this information handy will make it easier to replicate the experiments you ran in the past and those experiments whose details you might have forgotten about. Second, you want to keep track of the artifacts that you used during training. So these artifacts can include a number of things: training data, testing data. It could be other models. For example, which version of Word to Vec did you use? Or did you use a model to generate a feature for your larger model? Third, you want to keep track of metadata like hyperparameters, random seeds, training duration, number of epoch, activation functions, so on and so forth. And fourth, obviously, is you want to keep track of the results from your experiments. This includes metrics like mean absolute error, mean squared error, F1 log loss, et cetera, et cetera. That way you have visibility into how each individual experiment performed. So if you have all of this information available with you along with your source code, then you don't need to run the code from start to finish to find out what happened. It's all right there for you. So jumping into the next slide, you might be wondering, how should I be tracking all of this? You might start off manually writing everything on Post-it notes in your notebooks to a text file, or logging it all to a console output or some rudimentary mechanism like that. But it's obviously not an efficient practice, and it doesn't lend itself well to scalability or reproducibility. And in the next slide, you can see here something that's a little bit more disciplined. You might use a spreadsheet to track everything. Like this one here, which honestly isn't that impressive or sophisticated, but you're keeping track of and managing all this extraneous metadata. And even though it might seem too tedious, it might feel like it just creates more overhead and cognitive overload. And you probably feel like you don't need many of these bits and pieces of information, but you won't realize that you need it until you do need it. And because the time will come when you have to go back to that experiment after a week, after a month, after a year, or you want to bring on collaborators or share your work with somebody else. And when that happens, how's that person, whether that person is a future you or a present day collaborator, how are they supposed to figure out the end-to-end process of how that experiment was run? So there's a lot of tools out there that could help you with this. So I recommend Comet. I'm obviously a bit biased, but if I didn't think the product was awesome, I wouldn't be working here. So it's free to try. So why not give it a shot? You can check out the Python quick start guide or the R quick start guide. Both of them will get you set up fast. But once you've got the tooling to help track all of the experimental runs, you can start iterating and experimenting with algorithms. So over here on the next slide, baselines again. So I think we kicked off the series, maybe it was the second or third series, we were talking about the importance of baseline. As a quick recap, you establish a baseline by trying a simple model for your task. And this could be simple heuristics, it could be a dummy model, linear, or it could be linear or logistic regression. And you do this so that you can get a sense of whether the problem you're working on is tractable or not. Then once your baseline results are established, then you can start conducting an initial set of experiments with more and more complex models. So how complex you get is going to depend on the problem you're trying to solve. You might want to try boosted trees, Gaussian processes, neural nets, or any algorithm you think would be applicable. Whichever one you choose, start off with off-the-shelf configurations for those algorithms, and don't worry about tuning hyperparameters or applying any type of regularization at this initial stage. It sounds counterintuitive. You want to see if you could build a model that could overfit your training data. So going into the next slide, a bit of a thought experiment here. I want you to imagine that you sampled 1,000 examples from your data set. And let's just suppose that is 10% of the total data set. First thing you want to, once you've got that sample of the data set, the first thing you want to do is run your feature engineering pipeline on those samples and then try to overfit your model on them. Then you want to iterate over different combinations of features and try to identify which are most impactful for driving model performance. And then finally, you want to compare your training metrics across the model types and the features to verify which types of models have the capacity to learn from the data at all, right? And next slide, you might be wondering why. Why are we doing this? Well, you're doing this because you want to verify that your training and evaluation setup is working as expected. And specifically on the next slide, it's a laundry list of things that you want to verify. So you want to verify if your data is being loaded in the correct way for the model to consume. You want to verify that all the relevant metrics for the modeling task are being logged, or do you have new ones that need to be defined? Verify whether the splits in your data sets are valid. Is there any leakage between training and validation sets? You want to verify if the results can be reproduced when running the same experiment, or verify if there are any discrepancies caused by incorrectly setting the random seeds. You also want to verify if the label and the prediction match up perfectly. So once you're confident that the training and evaluation is trustworthy, then you can start slowly ramping up the complexity of the model. So on the next slide, you're probably asking now, why does all this matter? Okay, let's say that you're working with a neural network. All right, you might want to try to train on a single data point or a single batch and see if you're able to get an error as close to zero as possible. And then check if the prediction and labels align perfectly. If this isn't the case, then that indicates that something's wrong with your model architecture. So you would debug this by logging weights, gradients, and activations in the model and inspecting whether or not these are changing over the training process. And once you're able to find a set of models that are able to overfit on your training data, you can try regularization approaches to improve the model's ability to generate. So for your regularization experiments, you could try things like investigating the effects of scaling the amount of data on your model. You could track how the training and validation metrics for each model type change as more samples are added to the training set. And just as a refresher, some examples of regularization that could include L1, L2 regularization, early stopping, dropout, things like that. But then after this initial set of experiments, you should have enough information to identify the most promising algorithms and feature combinations. So these initial set of algorithms will now move on to further development. So at this stage, you should have an idea of the types of models that are able to fit your data, the features that work best for each model type, and the effects of scaling the data on each candidate model type. Then once you do that, you're ready to start with the hyperparameter tuning, which we'll talk briefly about in the next slide. So you don't want to spend an unnecessary amount of time tuning hyperparameters. So a good way to start is by using the sample data set to quickly iterate over different hyperparameter configurations. So your results here are highly dependent on whether you can get a representative sample of the data set. If the data is complex, then this could be much harder. So one workaround is to investigate the effects of adding more, investigate the effects that adding more data has on performance. Maybe you're looking at the top end number of hyperparameters with just your sample data. You can use a heuristic to compute. You can use a heuristic of compute resources rather as a way to determine what threshold for that end should be. So to avoid overfitting the sample data set, just try to build multiple validation sets by sampling with the replacement from the full validation set. Then average of these results from each set would be an indicator of the performance of the hyperparameters on the entire validation set. So you just want to be as methodological as possible when searching your hyperparameter space. So you might want to start simple using a search algorithm like random search. Random search, it's a solid baseline for optimization techniques. And depending on the problem that you're working on, you might want to use Bayesian optimization methods, which Comet has built into the product that can really help automate that process for you. And once you start using these more complex kind of optimization techniques, you're able to fine tune and narrow your search space. So, just make sure that you're starting with a wide range of values for each hyperparameter. You want to sweep across a wide search space, and then you can use discrete values for the parameter options. So even if your hyperparameter is like a continuous variable, learning rate or momentum or whatever, it's much more efficient to narrow down a range of values before search a continuous parameter space. So once you've got a set of hyperparameters that work well on your data, then you can start to fine tune your approach by maybe ensembling models together using the top performing models, or letting your model train for extended period of time, or you could try to further optimize your feature engineering pipeline. Next slide here. So I hope that you're able to see throughout this process that machine learning is not just when code meets data. It's when code meets data plus hyperparameter model architectures, random seeds, compute environments, evaluation metrics, and a whole host of other important considerations. But we could still adopt best practices designed to facilitate collaboration and automation of the whole process. And so my hope is that with this short lesson and the accompanying blog post that goes with this lesson, that we've done that we've shared best practices that we've learned with some of the best machine learning teams in the world. So the final slide here, just reiterating the point that machine learning is an iterative process with a lot of moving parts. Manually tracking the entire process, it's not only unnecessary to do that, but it's an unreasonably error-prone burden on yourself. People talk a lot about technical debt in machine learning, and a lot of that high interest debt comes from tracking. So everything from metrics, data set distributions, hardware details, et cetera, but it is in our best interest to automate this process as much as possible. And so the machine learning community can benefit a lot from the best practices used in traditional software engineering, leveraging automated tools, GitHub and CI, and making good use of version control, good use of pull requests, good use of CI tools and containers to run experiments. These are all great lessons that we can learn from software engineering. But that's enough of this presentation. I want to pause here, see if you guys have any questions, go ahead and drop them in the chat, and then we'll go ahead and jump right into our panel discussion, which I'm super pumped and excited about. All right, see some questions coming in here. How do these search algorithms and other hyperparameter tuning methods you all use perform when you have severely imbalanced data sets? That's a great question. I'd love to see if some of our in-house experts would love to help tackle some of these questions. We've got a couple of people that will be part of our panel coming up, Dhruv and Michael. And then also got Dr. Doug in the house. So it'd be an excellent opportunity for you guys to jump in here. So Dr. Doug, let's jump to you on this one. I'm curious if you have a response here for Marissa. So how do the search algorithms and other hyperparameter tuning methods perform when you have severely imbalanced data sets?
I must admit that every time I do a machine learning task, start with a new data set, start with a new model, I'm constantly surprised at what happens. I always learn something on a new data set or a new model. I don't know. That's a really good question. Dhruv, Michael?
Yeah, I'm also stumped as well. That's a great question. It's one I'd be happy to research and get back to you as well on which if Dhruv and Michael don't have any insights here.
Yeah, I'll say too that I think it's a very interesting question, and I don't know if it's something I've thought about along those terms before. But I'll say this: if you think about if we look at the sort of hyperparameter tuning domain for this question, and we're saying like, how does something like random search versus like a Bayesian kind of optimization algorithm compare for imbalanced data? I'm inclined to think that you're not going to see a huge difference like on the basis of balanced versus imbalanced data for those two. I say that because as I see it, that search algorithm, as you're passing in different combinations of hyperparameters, generally getting the entire data set, I would say dealing with, I don't know, my first inclination is that like dealing with imbalanced data in this setting is like more, you want to be very mindful of your, let's say like cross-validation strategy. Like it's very typical that you might go for like stratified cross-validation rather than naive cross-validation. So that way, when you're choosing your folds, you maintain a distribution of, you maintain the class distribution across those folds to avoid the sort of sampling error introduced by imbalanced classes and naive cross-validation. Yeah, that's the first thing that jumps out to me, is that's really where, that's where my mind goes. But I'm interested in looking into the literature more and seeing if like choice of optimization method like factors in much when you have imbalanced classes.
Yeah, definitely. Marissa, if anything, you've given us a great topic for a future blog post. I think this is a great thing that we can run experiments on in Comet and write about. So thank you so much for seeing us with that. Dhruv, you got any comments to this insight into this question?
Yeah, I think with most, as with most questions in ML, my answer is it depends. You can do many things. One of the things that Michael touched upon was the stratified sampling. So if you're doing cross-validation and running a hyperparameter search, it's not necessarily the hyperparameter search algorithm, but more your experiment design that might help you in this case, because really with hyperparameter search, you can tune really anything, right? So there are methods to deal with imbalanced data, which is like you could do upsampling, you could do different types of oversampling, and those sampling methods also have parameters that can be tuned. So in that case, it's like you could tune set your random search to tune the sampling parameter, and you could also ensure you have some sort of holdout set that is representative of your evaluation or validation set and test against that. I don't think there's like a definitive answer. It's sort of case by case basis.
Yeah, definitely a point of experimentation, I think, for machine learning. Great question, Marissa. Another good question. I like this question a lot. And I know the answer to this is going to be, it depends as well, but I'd love to get some of the breadth of experience here from Michael, Dhruv, and Doug to chime in. But from the time you have the data in hand to the time you produce your first machine learning results, what do you think a good turnaround time is? Yeah, that's a good question. So it depends on how big your team is, how powerful compute resources you got, how complex the problem is. I'll say from my experience, I think the longest time it took me to build a model, just because I was the only one doing everything. This is from discovery, talking to internal stakeholders, to figuring out how they look at the problem space, and then creating features, and then iterating over models and stuff. It took me about 2 to 3 months just to prototype thing, and then another month and a half, 2 months to get it deployed, 2-3 months to get it deployed. So that's my experience there. Doug, I'd love to hear from you, and then maybe we can go to Michael and Dhruv.
Yeah, that's an interesting question, and maybe it has a bit of a bias towards recent machine learning experimentation. But if you were to take that same question and apply it to all of science, you realize that that's probably not the right question to ask. Say you take some unsolved or even a solved problem in science, and say, how long do you think it'll take to really take the problem and then turn out with an answer that you could put in production? And the answer may be, it's not possible. It's just not a problem that machine learning can really solve. But on the other hand, it might be that you can create something that is usable, but then there are a lot of edge cases that you need to deal with. So it's really just a huge problem. And to come up with an idea of a basic turnaround time, I think is the right question. The wrong question.
I'll hop in
Michael,
really quickly and touch on Marissa. I saw you mention in the chat that this is sometimes a hard sell when talking to execs or other business stakeholders. And I'll say this: you I guess gave your question like with having the data in hand as like your step one. So hypothetically, if you have some data in hand, you could make an awful model almost immediately. And in my experience, I found it helpful to introduce possible like pitfalls and like feasibility issues and stuff like that through the context of, here's a concrete, very bad model that I've made. Here's why it's a problem. So it's almost like a little bit more cynical of an approach to why baselines are helpful. You have a concrete unit of work, so to speak, and you can say, all right, if we do nothing basically, and we make the most naive model, we'll run into these problems. And I think as a rhetorical strategy, for some reason, like a lot of audiences feel like problems exist more if there's a real but very dysfunctional model, even though you might already have identified those problems before you built the model. So I would say if asking for more kind of runway time to build better models is tough sell with execs or other business people in your, for me, it's always been helpful to like basically make the worst model I can to start with and say, this is what the problems are, like in a sort of like concrete, positive, like they actually exist right here. I can point to them versus I know that they will exist if I don't try to fix them.
Excellent tips. Thank you so much, Michael. Dhruv, any additional feedback here?
Yeah, I agree with I do agree with Michael. I'm more and more becoming a proponent of like get to production as quickly as you can, even if that means putting into production like a heuristic or baseline model that just outputs a single value for your classification or regression, whatever the task is that you're trying to solve. You learn things about the data in production if you do this, and shouldn't take you a lot of time. Because if you have a model that's like only outputting a positive class or a negative class, you can say with certainty, if we only guessed just the positive case, we would be right 70% of the time. Sometimes these results can be surprising. And the faster you get to production, you can identify like issues in terms of like how data is changing over time. So you get an idea of the volume of data coming into this model, drift, those sort of questions like fairly get answered like fairly early on. So you can anticipate things like, okay, if I were to make a better model, how often would I have to retrain this model? Or yeah, that's like my point, like as quickly as you can. So it could be just a few weeks if you have data in hand.
Marissa, thank you so much for those great questions. Really appreciate that. So now let's go ahead and get into our panel discussion. I was going to introduce our panelists, but I'll still go ahead and introduce them. But first panelist I'll introduce is my fellow colleague at Comet, Dhruv. So Dhruv is experienced in creating software tools for researchers in industry, research and development environments. He focuses on novel, high-impact technologies. He's earned a bachelor's in mechanical engineering from Georgia Institute of Technology and a master's in mechanical engineering from Columbia University in New York City. Prior to joining Comet, Dhruv was a research intern and research engineer at IBM. Dhruv, thank you so much for joining us here. Our next panelist is my fellow colleague at Comet, Michael Cullan. Michael's interests in machine learning range from computational paleobiology to AI for collaborative jazz improvisation and really everything in between. He's earned a bachelor's degree in mathematical statistics and probability from the University of Arizona with honors, and a master's in computational statistics from Arizona State University. In his free time, Michael applies his math and programming skills towards creating code-based visual art and design projects. He's also going to be hosting a upcoming series of panels on reinforcement learning with some industry practitioners coming up in the next few weeks. So please keep an eye out for that. It's gonna be a lot of great content there. Michael, thank you so much for joining us. So if you guys have not yet got a chance to join in on the working sessions. They are all hosted on YouTube. We'll leave a link for you right here in the chat on both on LinkedIn and right here in Zoom. But I want to take a moment to pick Dhruv and Michael's brains on their approach to the working sessions. So we've been talking a lot at a high level over the last several weeks about the machine learning process and managing experiments and reproducibility and baselines and all that stuff. But we've also on the back end been doing a lot of this stuff with practical code-based examples that I encourage you guys to check out. So today we're just going to take a little bit of time to chat about that. So I know you guys, Dhruv and Michael, go into the project into great detail during those working video sessions. But just at a high level, can you describe the problem statement that you're trying to solve with this project? So let's hear it from you on this.
Yeah, the idea with these working sessions to supplement all the great stuff that we've been talking about in the Standardizing the Experiment series is just like how it started was like Michael and I had this discussion where we've seen a lot of papers about how to outline this process, but there are a lot of like messy details in the reality of building a model with a team that aren't really highlighted or showcased. So we thought that we would, while these sessions are going on, have a sort of sidebar that goes through the process of building a machine learning model for like made up business objective, right? So our business objective is given a title of a post on Hacker News, we want to predict using a model how high it will score or how well it will do in some way. And like the higher level business objective is like we do well, maximizes traffic to our site, we get like click-through rates, views, and hopefully other things will follow. Yeah, and then the sort of nitty-gritty of the video is that it covers like how to structure your code repo, how to collaborate with someone using Git branches, more like formal software development methodologies, and all the while using like Comet as a way to keep track of all your experiments. And so at the end of all the work that you put into this model, you have reproducible workflows, and you know exactly what path you took to get to this model that finally made it to production.
And talk real quickly about the data source that you use to build this example out.
Yeah, there is a public Hacker News dataset on BigQuery. I think you have to sign up. I think you can just use your Google account, but you have to sign up you can get your BigQuery credentials, and I can find the link and drop it in here in a second, but it's open and anyone is free to access it. So it's all the Hacker News posts, including comments, all the way back to 2014 or 15, I believe. And we are going to be analyzing the years 2018 and 2019 as our training data, and then using the data from the year 2020 as our evaluation set.
Drew, thanks so much for that. And you all took a couple of different approaches to solving this problem. So Michael, can you describe why it's beneficial to frame your problem in a couple of different ways?
Yeah, absolutely. Thanks, Harp. So we took this initial ambiguously defined business problem of can we predict article popularity or success, or maybe success rate or something like that. And we want to do that based on, as Dhruv mentioned, based on the headline and perhaps some temporal information when we're posting and things like that. And if we go by what's just in the raw data, predicting popularity might mean there's this score that we have that comes from upvotes on articles. So predicting that score would be making a prediction on a continuous target variable. And so we're doing regression. And that's great because we could definitely imagine our stakeholders asking, hey, I want to know how many upvotes this is going to get. And so being able to provide a prediction on that literal value is desirable. It's nice in a lot of ways. We also like to leave other avenues open for like other types of reasoning that maybe are more in line with what someone's like underlying concerns are. So if someone says, I need to know how many likes this article is going to get, is that because they need to know the exact number, or is that because they need to know whether or not something will be successful or along some sort of grading scale of success? It may be the case that if we get at least 10 likes, which would put us, from what I recall in the data, in something like the top 5 or 10% of posts, if we get at least 10 likes or upvotes, that's a success for us. Now, if you frame it that way, which is the branch that I've been looking at for the last few weeks, so just doing a really simple kind of threshold-based transform from continuous response into binary classification, it opens up like on a really basic reasoning level. Now you can ask the question, like, what's the probability that we get at least 10 likes. And it might be the case that like that's more in line with the business concerns, the anxieties underpinning the problem, rather than just predicting the exact score, which might serve like vanity more. Ultimately, we've left both of these open. It's helpful to see like how performance is like relatively going across each branch of the project. And in a real world scenario, we would probably be prototyping both of these and then seeing which of them actually fit more into our collaborators' workflow. But that's why we took the dual approach of regression and classification.
Yeah, I found that to be really interesting. Same exact data set, same exact kind of business problem, but then just framing it as Michael took the approach, will this post be successful or not? And if you want to get more details on what he's defining as success, definitely check out the videos and check out the code. And then Dhruv is predicting whether or not, or rather Dhruv is predicting the actual number of upvotes that this would get. So I'm curious, I'm interested about the feature engineering aspect of this. Did you guys use the exact same features for each task, or did you guys use different features, or is that something that you want us to find out by watching the videos?
It's always a good time to plug the videos, but I'll say just briefly that we've used the same features. Dhruv did a little bit of feature engineering for the most recent working session. So building on top of our baselines, we decided what's an easy way we can incorporate some extracted features from the text. And so Dhruv got some text embeddings from those. I'll let you actually talk a little bit more about that, Dhruv.
Yeah, so I guess to add a disclaimer, like the goal with the working session was more to like showcase workflows and less to build the most optimal model, because we could spend weeks trying to engineer a good feature. So we went with what can we do in a relatively short period. The features we extracted were timestamp information. So I parsed the date, which is like in date time format if you're using pandas, into the day, the week, the hour, and the day of the week. So you get 4 numbers from that. And then the text features used basically a pre-trained BERT model and fed the text through the BERT model. It outputs a bunch of embeddings, average those embeddings, and that's like your title embedding, and that's the only feature. And so we're going to experiment with those features, and then we'll see if we can even beat the baseline, if these features even help us beat the baseline before we invest more resources. Another thing we did for the feature engineering is we sampled the data. So the entire training data set is close to 1 million records. And if I were to run, like, because I was using Transformers library and like it's a neural net, like if I were to run that on 1 million records, that's a lot of compute time. And at this stage, I'm not necessarily, I'm exploring, right? So I want to be able to explore things quickly. So I don't want to wait around to compute a whole bunch of features that might end up being useless. So what we did was we sampled about like 5% of the data set, and we use a stratified sampling. And so you can stratify sample a continuous variable. So what we did is we binned the target into a bunch of quantiles, so like 10 quantiles. That's an arbitrary, that's a hyperparameter, but like that's a place to start. And we stratified based on these quantile bins. So even though we did sample only 5% of the data set, the target distribution is the same. And because we're using a smaller data set, we can run our feature engineering faster, we can run our hyperparameter search faster on this data set. And the idea is the relative performance of the different models should be the same. So as you scale up the data, this performance should hold. So if you have like hyperparameter configuration A is the best on your 5% sample, it should still be the best on your full 1 million records.
Thank you so much. And something that kind of sets the tone for the entire series, maybe not sets the tone, but an important piece of that was actually just repository structures. I just want to quickly talk about that. Why is it important? And I guess, why is repository structure important? And how do you find the right structure for the project that you're working on? Let's hear from Michael on this one.
Yeah, this has been an ongoing learning process for me over the last couple of years, making me jump out of being like totally overly reliant on Jupyter notebooks and some of the pitfalls that come with that. And I will say at times, I think I've overcorrected. I think notebooks are great, and I find myself like causing trouble by avoiding them too much sometimes. So nothing against notebooks, but yeah. So the idea here was that we wanted to keep every kind of all of the necessary code within arm's reach as we're iterating like in different directions. And so that means like if we're both going to be working on separate formulations of the problem, we want to ensure that we have like still the same data resources, that we're working with them in the same way, and that we can maintain and like further develop like other methods or like functionality like for handling data, for instance, without the two branches drifting too far apart. So that's one reason why it's nice to work in a super modularized repository. It also just lends itself better to reproducibility. I don't know, gettable, to use like a silly word. And that was like big stuff. In terms of like why we chose the structure that we did, we wanted to go with something that we could keep building on as we developed. So like, for instance, under kind of our source directory, we split things up into like vague, or not vague, but like basic categories of like functionality, right? So there's like a file called train.py, there's data.py. And maybe as more functionalities built into like how we handle data, we start having to have like more stuff in that module that becomes a directory, not just a script. And so we can further refactor like data handling code. And one nice thing about like one thing that we can do to keep that smooth is like if we're working in very Python friendly IDE like VS Code, which Dhruv and I are both using pretty consistently, and definitely I think it's what we've both used for this project. If you play your cards, the Python extensions for it are very nice when it comes to if you are refactoring and like name changing, it'll actually change names throughout your code. That's been the idea, is that we just want to keep building it as we go along and like adopting a structure that's easy to navigate and easy to keep adding to as the project grows.
Michael, thank you so much. A great question coming here from Shuaib, saying for folks over here at Comet, if you had one tool to focus or choose for ML ops for beginners, i.e. frameworks, Django, Flask, testing methodologies, PyTest, CI/CD, software tools, or ML frameworks, what would it be? I'd say it would be Comet if I had to choose one. Let's hear from you.
So if I understood the question correctly, it's like, what tools or frameworks should you get started with when trying to adopt like a more ML ops type of workflow? Is that,
yeah?
Have I got that?
Yeah, that's what I'm getting from there too. The question was, if you had one tool to focus or choose for ML ops beginners, frameworks, testing methodologies, software tools, ML frameworks, which would it be?
Truly, like I'm gonna go very old school with this and say Git. Get good with using the command line, and yeah, and knowing how to write good tests is beneficial no matter what, because really at the end of the day, as like ML practitioners, our tools are code, right? Like our primary output is like we produce code, and the data and the code produces data and all those other things. So being able to write like readable code, testable code, I think goes much further than any sort of framework or one specific type of tool, because like tools and frameworks change. That sort of fundamentals are forever.
Yeah, that's 100% true. Thank you, Dhruv. Michael?
I was going to have kind of the same answer. I was also leaning towards Git and like towards those fundamentals, Git and the command line. And I suppose if I had to add my own angle to this answer, maybe I would try to skirt the question a little bit and say, for me, my preferred way of learning is by contrasting different options and seeing like what frustrates me or what problems I run into with contrasting approaches. So for learning ML ops, for instance, like if you were like if you were cared about, for instance, like deploying models and how that maybe relates to managing virtual environments, or like generally like how you're going to package models, I would say it's really helpful to try a few different things. See the way that you handle dependencies with Conda versus virtual M versus poetry versus like a whole bunch of 2 or 3 different things, and then see like what is frustrating about each of those. And honestly, I think following just like those kind of chains of frustration is the most enlightening thing, because like ultimately good ML ops work is about like mitigating friction, and you have to figure out what that friction is before you can do anything about it.
Really, really insightful perspective, Michael. Thank you. Yeah, I've never considered trying to do things that are not delightful to find the things that are delightful. I think that's a great way to frame it. Recall a few weeks ago, we did a session about understanding and validating your data. We had Dr. Abe Gong as part of the panel discussion, who's from Superconductive, the company that's behind the Great Expectations. And as part of the working sessions that we have, Michael did a really in-depth, awesome walkthrough of how Great Expectations works within the context of this project. I'm wondering, Michael, with respect to the validation aspects of the project, like what were some of the challenges that you faced?
Yeah, absolutely. I will say this, taking on something like data validation, and as I was like looking to build examples for using Great Expectations for this project and stuff like that, it's not a light undertaking, and it requires like a lot of examination and collaboration. And really, at the end of the day, like your gold standard is domain knowledge for what makes for reasonable assumptions and expectations about data. I think scaling up like that part of this project, I think would really involve like bringing in more people to have like more like direct conversation about what we expect the data to look like and what happens when it looks wrong. But I will say that Great Expectations was super, super helpful, like setting up a data validation framework for this. And for anyone watching who has not tried messing around with Great Expectations for making like data testing frameworks, definitely check it out. It's super cool. And I'll say this as well, that Great Expectations has a really like elegant and effective like overall approach, which is that as you start building components to make like your data validation schemas, it actually generates a lot of Jupyter notebooks and then walks you through them, because the shorter feedback loop that comes with notebooks can be really helpful when you need to like look at data while building configs and stuff like that. And for anybody who has ever had to dynamically generate Jupyter notebooks, I don't know if this has ever come up in any projects you're working on. It's coming up in something I'm working on for Comet right now. Great Expectations has like a very compelling and sophisticated approach like in their source code for how they're doing that too. I think stuff like generating notebooks to make other people's lives easier is pretty cool. I really like how Great Expectations does it, and I have adopted some of their methodologies and how they actually make their product too, as we've been shaping Comet.
Thank you very much, Michael. Drew, thank you for hanging out. I know you've got to get going. You got another meeting, but I appreciate you being here.
Yeah, thank you, Harp. Thank you, everyone, for joining. Great discussion. Really enjoyed it. Yeah, look out for the next working session. Should be out pretty soon.
Definitely. Thank you. And Michael, while I have you here, why don't we give us a sneak peek of what's next in the project, Michael? I'd love to get people excited and enticed about checking this thing out.
Yeah, absolutely. What's coming up next in the Hacker News project is, like I said, we're expanding on our baselines. We're starting to talk about workflows for using the Comet optimizer for hyperparameter sweeps and building out some non-trivial models. So I'm, currently doing a bunch of sweeps over different configurations for like gradient boosted trees and stuff like that on the classification side. And then from there, we might just spend a little round of refactoring and just like fixing up some parts of the repository that are starting to diverge a little bit, and just like work on tooling and workflow stuff.
Awesome. Thank you so much, Michael. You guys, make sure you check out the working session. So far, we've got, I think it's 4 videos. Each video is like under 20 minutes, and you're going to learn a ton. We got the accompanying code with it as well. That'll not only teach you how to be a better ML engineer, but you'll learn a lot just from watching these guys talk about the project. So definitely check it out. And don't forget to join us next week. We got the last session, the last part of the office hour series, rather. We're going to be speaking to in-house experts at Comet. Will be Michael and Drew, who will both be back. Dr. Doug will be back, and then our head of product, Jacques, will be on as well. We're going to talk about the last mile of machine learning, which is all about serving and monitoring your model in production. It's going to be an exciting way to wrap up the series. So hopefully you guys are able to join us for that. Thanks for joining us today. Hope you guys enjoyed it. Hopefully my background and these chirping birds weren't too distracting. So thank you guys for joining us. Remember, as usual, you got one life on this planet. Why not try to do something big? Cheers, everyone.